the lambdas. So let's see if we can get a lambda. Did we ever solve for a lambda? Oh, yeah, we did, right there. There it is. OK, so if lambda is 2 over x, in this case, it would be 2 over 2, which means lambda is 1. And then same thing for this one, it would be -1, wouldn't it? OK, we're done with that. That's what happens if x is not 0. What should we look at next? What if x is 0? We never looked at that, did we? OK. So let me change this. Suppose x is 0. Now you can't solve for lambda, can you? If x is 0, what can you tell me? Y squared equals 13, right? But you've got another problem. Look at your first equation. If x is 0, what's your first equation say? Equation 1 says that 2 is equal to 0, right? And it's not. Which means x can't be 0, OK? But you had to think about it, because if you just, I heard someone say it, and that's OK. If x was 0, yes, it would imply that y is going to be, what, square root of 13 plus or minus? But see, x being 0 does not satisfy this equation. It has to be all three simultaneously. OK. Anything else that we didn't look at? What about taking equation 2 and solving it for lambda, and then taking that and plugging it into this one? So what would I have to start my suppose off with? Suppose y does not equal 0. Right? If y does not equal 0, I can take my second equation and divide through by y. So that would get 3 over y equals lambda. And then I could plug into equation 1 with that. And my equation would be 2 equals 3 over yx. Starting to look a little familiar. This is what we did just a second ago. Clear the fractions. We get 2y equals 3x. And then I can solve this for x or y. I'm going to solve it for x. 2/3 y equals x. Isn't that the exact same thing we had earlier? Isn't this the same exact thing? So this is going to, from here on, it's going to be the same result. Right? Same result. We're going to have this right here. Because you're going to replace x squared with 2y, or 2/3 y. And then you're going to square it, and it's going to become 4/9 y squared, and you're going to move through the same thing, right? OK. Is there anything else? You're going to have to do some jumping jacks or something. Yeah. Come on. Just go walk around or something. Is there anything else that I have not addressed or have not looked at? If y is 0. So yeah, what if y is 0? Suppose y is 0. Then what? Equation 2 says 3 is 0. That doesn't happen, so y can't be 0. If you do this, you can do that symbol right there. It just means contradiction. If y is 0, you get a contradiction. You're saying that 3 has to be 0, and that doesn't work. So these are two arrows hitting each other like that. OK. See, this is where this is the part that makes this difficult, is have we covered all the different possibilities? Yeah, I think so. Oh, you know what? Could we solve this for x and solve this for y? Could we? OK, so suppose what? If I'm going to do that, then I need to suppose what? Suppose lambda is not 0. All right? Suppose lambda is not 0. What would equation 1 tell us? X is 2 over lambda, yes? What would equation 2 tell us? Y is 3 over lambda. You with me? Got it? Keep going. What now? Plug them both into 3. So go into equation 3 now. What's x? 2 over lambda. Square it. What do you get? 4 over lambda squared. Plus, plug y into this. What do you get? 9 over lambda squared equals 13. All right. Put these together. You get 13 over lambda squared because they have the same denominator. And now just multiply both sides by lambda squared, which we can do because lambda is not 0. So you'll get lambda squared is 1, which means lambda is plus or minus 1. Have we done that? We actually did that already. Look at. See, you could almost look at this as in, look, those are all the, this is like, what if you had just started with this, said, hey, let's just assume lambda is not 0 and solve for x and y. You could have started the whole problem like this. And then you would have got lambdas plus or minus 1, and then you would have from that been able to come back and get what x and y were. So, I mean, there's just so many different ways. It's hard to finally get to a point where you're like, yes, I've checked everything. I've covered all the bases. Done this, all right? I'm just going to put done. We've checked that already. Anything else? Suppose lambda is 0. Contradiction, right? If lambda is 0, either 1 or 2 are going to be a contradiction. So lambda can't be 0. I'll put it down here. Suppose lambda is 0. Then this is the same thing, isn't it? Okay, that's it. It was a little more involved than the last problem, right? Yes?
Do you prefer solving it one way over the other?
No. My preference is that you cover everything you need to cover, and it doesn't matter which way you do it. I don't like grading these. It's very difficult to grade these. So I am looking for logical steps. You notice how I'm like bracketing out each of my, like suppose, bracketing it. The next problems are going to get even more challenging. And so what we're going to have is like within one suppose, we're going to have another like 2 supposes that break off to be like 2 more supposes. So we're going to have like these branches of ideas. And that's what I hope to see from you is some sort of logical structure, not just random, algebraic crap all over the place. Because if you over here suppose y is not 0, and then over here you suppose y is 1, those things, am I supposed to guess, like, are they together, like y is not 0 and 1, or are you trying to let y be 1 and 0 at the same time? You have to get it all in order. If you try and do too much at one time and you're not, I don't know how to explain this. If you get lost in the problem, you might potentially be trying to let a variable take on 2 different values at the same time, which would be a disaster. All right, so I just erased the important numbers. What were they? I need to check f of 2, 3, 2, negative 3. That's it, right? Or negative 2, negative 3. That's it. Check. Most likely, that's going to be your max and min right there. One of those is going to give you a max, one of them is going to give you the min. So 2 goes in, 26. The other one, negative 26. I think it's probably obvious that that's going to be your max and min right there. Questions? Here's the picture. Here's the plane. Here's the restriction. On the ground, there's the restriction. Can you all see it? Here's the points from the restriction plugged in. And you can see where it hits the surface, right? And we just found the 2 points here. One of them up here is 26 units high. The one down here, 26 units low. Yes? Now we're getting into some nastiness. E to the xy is our function. Here are our constraint. Here's our constraint. X cubed plus y cubed equals 16. We should have Lagrange multipliers for sure because this is an equation, right? Constraint equation. We're not given an unrestricted domain, right? We're not given a closed bounded set. This is just a curve, really, right, on the ground. So 3 equations. Partial f with respect to x equals lambda partial g with respect to x. Second equation. Partial f with respect to y equals lambda partial g with respect to y. Third equation, constraint, x cubed plus y cubed equals 16. Once I set up the equations, I get to go solve them. So what is the derivative of f with respect to x? Y e to the xy equals lambda times the partial of g with respect to x. 3x squared, but then times lambda, right? So how about I write 3 lambda x squared. See, if you mess the partials up, it's over, right? I mean, pretty much at that point, it's done. All right, the next equation is partial f with respect to y, which is x e to the xy. And then partial g with respect to y is very similar to what we just had, except 3 lambda y squared instead of x squared. And then our third equation is there. All right. Enjoy. What do you want to do? Find an x, y, and a lambda that make all 3 true at the same time. For those of you who've studied matrices and linear equations, systems of linear equations, we understand that there's a very systematic approach to solving systems of linear equations. It's called Gaussian elimination. Computers are really good at it because it's just do this, just operations, addition and multiplication. That's all it is. Systems of nonlinear equations, much more difficult to do. And you have to do them by hand and check a lot of different scenarios. So, all right, what do you want? You want to solve? I heard solve for what?
We could solve for x or y because we know that e to the x and y cannot be 0.
Yeah, but that's not equal to 0.
But if we divide by e to the x to the y.
Okay, you want to divide both sides by e to the x to the y.
That's what I'm saying.
Because you know that that will never be 0.
Right.
That's fair. We could do that. You want to divide both sides by that? Okay. I have no problem with that. Let's do it. So you want to divide. What's being suggested here, but hold on. Let me ask you before you put your pencil to paper on this. That's what I would get, right? But that's solved for y, but it's in terms of y still, right? Like to know what y is, you have to know what y is.
What about solving for e to the xy?
You could solve for e to the xy
The equation.
on both of them. Or say again?
On both of them.
Solve both for e to the xy. I heard solve for lambda. They're both good. Do you understand the difficulty here? If you solve this for y, you haven't really solved it for y. Because you still need to know what y is to know what y is. Right? Like if I have like x equals 4 plus 1 over x. Have you solved for x? In order to know what x is, you have to know what x is, right? So, all right, so let's take a vote. Are we going to solve for e to the xy on both? Or do you want to solve for lambda on both? E to the x, y? Lambda? Okay, let's show hands because I can't tell by how many. Okay, how many of you want to solve for lambda? Okay, e to the x, y. Wow, that's close. That's close. Okay, we'll go to the coin flip. So, no distinguishing marks. That's heads. Heads is lambda. Sorry. Heads was lambda. I should have called that. It's like the Super Bowl flip. Okay. It's going to be lambda. We're going to go for lambda. All right. Yeah, it didn't flip. All right. So if I'm going to take equation 1 and solve for lambda, then what do I need to say? Suppose x isn't 0. Suppose x is not 0, right? Equation 1 becomes that, right? Now, what would you like me to do with that? You plug it into 2? Or we could solve the other one for lambda also and set them equal to each other. I'm just going to go right to 2 in this one. Although setting them equal would be the same. But I will say this. If you solve the second one for lambda, you're going to also have to tell me what? Suppose y is not 0. So you're fixing them both then. I'm going to stick with just, right now, the only condition I have is that x can't be 0. That's the only thing I'm saying. All right, so let me rewrite this now. I might, at the end of the day, have to say that y can't be 0 either. But 3, here's lambda. Lambda is y. E to the xy over 3. Oh, I like that. It's going to cancel. And then y squared. Did y'all see that Diaz fight? That Conor McGregor-Diaz fight? No. All right, there we go. That I can do, right? Cancel those. What else could I do to make this a little bit nicer? Can I clear the fraction? Can I multiply both sides by x squared? Yes, because I'm saying x can't be 0, so that's a legal move. Right? If x is 0, then I can potentially multiply both sides by 0, and that's, you never want to multiply an equation by 0 on both sides. But x isn't 0, so this becomes x cubed e to the xy equals, what's over here? Y cubed e to the xy. Now what? You can divide out e to the xy now. I just told you, don't ever do that with a variable, but we all know that e to any power can never be 0, right? So I can divide this out safely without any concerns.
You see that I was seeing this.
Yes. Which means x cubed equals y cubed. X cubed must equal y cubed. So far, that's what I've got. If x is not 0, then to satisfy things, x cubed has to be y cubed. Now, where can I go from here? The third equation.